Hi, I'm Ed Rothberg, CEO at Gurobi Optimization. We recently released a new version of our product, version 8.0. I wanted to make a quick video to give you an overview of what's new in our latest release. Before I talk about what's new in the product, though, I actually want to talk about what's new at the company. In particular, we've actually hired 8 new people since January of 2018. So we've substantially increased the size of our team. And these people are spread out across multiple different departments in the company: development, marketing, sales, support, finance, admin. One thing I want to point out, though, is that we have not lost our technical focus. So among these 8 people, 3 of them have PhDs in optimization or optimization-related fields. So we now have 27 employees in total in 4 different countries: US, Germany, Chile, and Canada. This is a photo of the employees of the company from a recent company offsite meeting. All right, so let's talk about what's new in our latest release, version 8.0. So version 8.0 is primarily a feature release. So we've added a number of new features. I'll be talking about each of these in turn. So we added significant enhancements to our compute server and instant cloud products. We've significantly improved our MATLAB and R interfaces. We've added support for MATLAB problem-based modeling. We've added a new user partition heuristic. We've added support for multiple MIP starts, and we've added support for .NET Core. Despite the fact that this is primarily a feature release, this new release actually does include significant performance improvements. So towards the end of this presentation, I'll also be discussing the performance improvements in this release. I'll start by talking about the improvements to our MATLAB and R interfaces. One of our goals is to support all the most popular programming languages. So our product has provided interfaces for C, C++, Java, .NET, Python, MATLAB, and R. However, our MATLAB and R interfaces have always provided a subset of the capabilities of the other interfaces. So these interfaces didn't provide support for multi-objective optimization, solution pools, general constraints, several other features. With our latest release, these features are now available in our MATLAB and R interfaces. So these languages provide essentially all of the features of the other interfaces now. So one consequence of MATLAB and R having only a subset of the features was that we could actually only provide a subset of the examples. But with our latest release, now that all these features are available, we include a full set of Gurobi examples. So the MATLAB and R examples are basically the same as the examples for the other interfaces now. Another thing we've added is support for MATLAB's problem-based modeling. In MATLAB 2017b, the optimization toolbox added the ability to build optimization models in a more structured way. I've shown a simple example here. Using this new interface, you add optimization variables, you declare an optimization problem, you set an objective using an algebraic approach, you add linear constraints, and then you call a solve method. So these are all capabilities inside the MATLAB optimization toolbox. What we've done is in Gurobi, we've added the ability to call Gurobi from the MATLAB solve routine instead of calling the MATLAB solve functions. And the Gurobi methods are much faster and much more robust than the ones that are included with MATLAB. So there's significant advantages to being able to call Gurobi from MATLAB problem-based modeling. The next new feature I want to talk about is our user-controlled partitioning heuristic. Gurobi includes a number of heuristics that are designed to find high-quality solutions to MIP models quickly. Among these heuristics, I think we have 15 different heuristics. The most effective one by far is one called RINS, Relaxation Induced Neighborhood Search. RINS is what's called a submip heuristic. Basic notion here is you take your original problem and you take a feasible solution to that problem, your incumbent. And then you fix some of the variables in your problem to the values they take in the incumbent solution. And then you take that problem and you solve it as a MIP. So you recursively solve that problem as a MIP. And so what this does is it focuses attention on just a portion of the problem. So you're re-optimizing on just the variables that were left unfixed. The variables that were fixed through the incumbent solution are unchanged. So these submip heuristics in general, and RINs in particular, these are very effective techniques for finding high quality solutions to MIP models. The thing about RINs, though, is it chooses these subproblems, these portions of the problem to re-optimize. It chooses them automatically. The user has no control over how these choices are made. So with this new feature, with this new user-specified local improvement heuristic, if you as a user, if you have domain information, you have knowledge about your problem that might help to specify interesting neighborhoods to explore, you can provide that information to the code. So to give a few examples, let's say you're solving a problem across multiple time periods. So you as the user can say, please explore local improvement schemes that improve within each time period. So you fix the solutions for all but time period 1 and re-optimize just for time period 1. Or you could specify a window of time periods. So re-optimize for time periods 1 through 5 and fix periods 6 through 24, for example. Similarly, if you're doing something like production planning and you've got multiple machines, so you can fix what happens on all but one machine in the factory, and then you can just re-optimize on that single machine. So perhaps resequence the jobs on that machine. Similarly, imagine you're solving a problem that involves some geographic region. So you could consider re-optimizing within subregions. So you could re-optimize just within, just the Western US, leave the rest of the US fixed, or just within the Eastern US, etc. So this new local improvement heuristic allows you, the user, to provide this information to us, and then we, the solver, will use this information internally to create these subproblems in order to re-optimize. The next new feature I want to talk about is our new support for multiple MIP starts. So we've always provided the ability for the user to specify a MIP start. A MIP start is a set of settings for the variables that you as the user know produces a feasible solution. What's new in this release is now you as a user can provide multiple MIP starts. So if you know multiple potential solutions, you can specify all those solutions. What's the advantage of providing multiple MIP starts? Well, truth is, if you have multiple MIP starts and you know that they're all feasible and you know the objective values for all these starts, it's actually probably just as good to take the one that has the best objective value, specify that as a single start rather than giving multiple starts. However, in a lot of cases, you don't actually know that your starts are feasible. You may have partial information, or you may just not have values for the continuous variables. So in this case, you can provide all of these partial solutions as starts, and we will figure out which ones are feasible and which one gives the best solution. And also, if you're using our distributed MIP solver using multiple machines, these multiple MIP starts will be distributed among the available machines, and so the computation of these partial MIP starts will go much more quickly. Another new feature in our latest release is support for Microsoft's new .NET Core. Historically, .NET has been a Microsoft proprietary platform. So .NET provided support for a number of different programming languages, including C#, Visual Basic. There's several .NET languages. However, the only supported platform for running these .NET programs was Microsoft Windows. Recently, Microsoft has released an open source .NET platform they call .NET Core. And we've modified Gurobi. We've extended the product to enable you to run .NET programs on the .NET Core platform on Windows, Linux, and Macintosh. Now I'm going to talk about some of the improvements we've made to Compute Server and Instant Cloud. So these products have undergone some pretty significant improvements in our latest release. We'll actually have a webinar specifically devoted to these products in the near future. For now, I'm just going to go over some of the highlights. So I'll begin by talking about improvements to our Compute Server product. As a quick reminder, our Compute Server product allows you to offload optimization jobs from a set of one more client machines to a set of servers, to a set of Gurobi Compute Servers. So you can have as many client machines as you like. They offload jobs to the servers. If the servers are busy, the jobs get queued. As the servers become available, they'll pull the next available job from the queue, so they'll do load balancing. The jobs have priorities, so the servers will pull the highest priority jobs from the queues. It's quite a flexible means of offloading optimization computations onto a set of servers. So we've made a number of improvements to our compute server product in this release. The first is that we've moved to standard communication protocols. So in previous releases of our compute server, we used proprietary communication protocols, which had some downsides. With the latest release, we've moved to HTTP and HTTPS, so standard protocols. So this improves security. So HTTPS is a known security protocol. It's quite safe. It's quite well understood. Moving to HTTP and HTTPS has simplified deployment. So these are known mechanisms. No need to open up unfamiliar ports, etc. And we've also improved robustness. So the proprietary protocol that we were using certainly didn't have any known significant robustness issues, but protocols that are standard, that are widely used, are just going to be more robust in general than proprietary approaches. Another thing we've improved is our clustering capabilities. So with previous releases, you were able to create clusters of machines, but these clusters were, for the most part, they were static. So you would set up a set of Gurobi Compute servers, and then that was your cluster. With the new release, you can dynamically add and remove nodes from the cluster, which just makes it much easier to scale up and scale down your compute resources. Another thing we've added in the new compute server is a new command line tool called GRB Cluster. It gives the user a tremendous amount of ability to monitor what's going on their compute server cluster. It gives the administrator a tremendous amount of ability to manage what's going on in the cluster. So the user using this tool can look at the status of the cluster, see what nodes are up, what nodes are down. User can get a list of all currently running jobs, and actually can also get a list of recently processed jobs. So they get historical information about what jobs have run recently. And the user can actually also access job logs, so Gurobi log files from jobs that are either currently running or recently ran. And also information about what parameters were changed in these jobs. The administrator can use the same command line tool to administer the cluster. So get a list of the currently available licenses, can abort running jobs, can bring nodes of the cluster down, etc. So a tremendous amount of control over what's happening on the cluster. And then another thing we've added is a new REST API. So you as a user, as a programmer, can actually write a program that gives you these same monitoring and cluster management capabilities that you'd get from the command line tool, but through a REST API, so through something that you can control yourself. Now we'll talk about the improvements to our Instant Cloud product. As a reminder, our Instant Cloud product, you can think of it as being a Gurobi Compute Server that you can launch on a cloud machine. We actually host it on Amazon AWS. And you only pay for the time you use. So if you shut the machine down, you're not paying for that machine. So since Instant Cloud is built on top of Compute Server, the new Compute Server brings a number of benefits for our new Instant Cloud. In particular, as I mentioned, we use standard protocols. In the case of cloud, we strictly use HTTPS. So this again gives better security, better robustness, and easier integration with your existing network infrastructure. We've also improved your ability to manage your machines, your cloud machines, or your pools of cloud machines. So what I'm showing here is a screenshot from cloud.gurobi.com, which is the web interface for managing your cloud instances. For existing cloud users, this screen probably looks familiar, but we've added some significant new capabilities. First one I want to highlight is pool scaling. So a pool allows you to pre-configure a machine or a set of machines for use together on the cloud. The new pool scaling capability allows you to dynamically increase or decrease the size of your pool. So if you have a pool of, for example, 2 machines, you find that you have a very long queue of jobs, you can increase the size of the pool to 4 machines or 8 machines or what have you. And then when the queue reaches a more manageable length, you can reduce the size of the pool using the same capability. Another thing we've added is the ability to monitor various metrics about your machines. So you can see for each machine the current CPU usage, the current memory usage. This just gives you a better sense of what's going on within your machine pools. Finally, we've added significant new capabilities for monitoring jobs. So for example, you can get a list of jobs that are currently queued, currently running, jobs that are processed recently. We also have a new job dashboard. That's the screenshot that's shown here. For existing cloud users, this will be new to you. This is a brand new screen. And this gives you detailed information about jobs that are currently running, including information about the model that's being solved. So how many rows, how many columns are there in that model? Information about parameters that have been changed. For MIP models, it'll actually give you a graphical display of the progress towards finding an optimal solution. And we'll also show you the log file of the current running job. So you can use that to also get information about progress. And this is dynamically updated. So as the optimization proceeds, you'll get updates to the progress metrics, to the log file, to the graphics, etc. And finally, we provide information about job history. So you can activate a new archive feature that allows you to get information about jobs that have run in the last 3 months. Things like you can look at the Gurobi log files for all these jobs. You can get information about the completion statuses of these jobs, etc. Optimal, infeasible, etc. So a tremendous amount of information available about jobs that are both currently running and jobs that have run in the recent past. So we've significantly improved the capabilities of our compute server and cloud product with this latest release. As I mentioned, Gurobi 8.0 is primarily a feature release, meaning most of our attention went to adding new features to the product. However, there are still some pretty significant performance improvements in this release. The improvements aren't as big as the improvements we got in version 7.5. However, I think you'll agree that there's some pretty significant improvements in this release as well. So I'm going to talk about those now. When we talk about performance improvements, we have to talk about how we measure those improvements. And ultimately, the way we measure improvements is through benchmarks. Benchmarks are sets of models where we compare one version against another and look at the impact of a new version of the product, a change to the product, basically any delta between the two versions to try and understand what the impact is. So we think about benchmarks in sort of two contexts, internal benchmarks and external benchmarks. In the case of internal benchmarks, what we're doing is we're comparing one version of Gurobi to another version of Gurobi. The intent is to essentially make sure that we're heading in the right direction. Make sure that when we make a change to the product, it actually improves performance. So our internal benchmark is done on a set of models that we've collected over the years. These are academic models, public domain models, customer models. And for MIP, we've got a set of about 4,500 models that we use for our benchmarking. And we view these internal benchmarks as the most important benchmarks we do. So ultimately, we're looking at a very fine grain at whether changes to the code are improving the product or making it better across this wide set of problems. The other type of benchmark that I should discuss are what we think of as external or competitive benchmarks. And these are benchmarks that compare one company's product to another company's product. So Gurobi versus simplex, for example. So a professor at Arizona State named Hans Mittelman maintains a set of these benchmarks. You can go to his website and look at these benchmarks. So he's got benchmarks comparing different solvers for solving LP models, MIP models, QP models. He's got quite a wide variety of benchmark tests he does. So these give interesting information, but we actually consider these to have some pretty significant limitations. Generally, the sets of models are quite small, and the sets are pretty static as well. So over time, what winds up happening is the different solvers wind up effectively tuning for these small benchmark sets. So again, we view these as less important than the internal benchmark sets. And I should say we're in a good position to say that these are less important, that you shouldn't pay too much attention to these, because we in fact win almost all of these benchmarks. So the point is that we put a lot more weight into the results from our internal benchmarks than we do in the results of these external benchmarks. So in the case of Gurobi 8.0, I'm actually not going to show the external results, mainly because we just released 8.0. Hans hasn't had a chance to run our code, and so these external benchmark numbers just aren't available yet. So let's look at performance results for our latest release using our internal benchmark set. So before I present performance results, I just wanted to give you some additional information about our benchmark set. So this is a scatter plot showing information about the 4,538 models in our MIP benchmark set. Along the x-axis, you have the number of rows in the problem. Along the y-axis, you have the number of columns. And each blue dot represents a single one of these 4,538 models. People often ask us if they have a MIP model, they ask us, is this a particularly large MIP model? How does it compare to the set of models that you typically wind up solving? So this graph gives you some indication of the typical sizes. So I've drawn red lines on the chart to show the set of models that have more than 100,000 constraints and variables, and also the set of models that have more than 1 million constraints and variables. And what you can see is that there are many models that have more than 100,000 constraints and variables. So people are solving models of this size quite routinely. However, you can see that the number of models that contain more than 1 million constraints and variables is not that large. So once you're solving models with millions of constraints and variables, you're solving models that are among the largest, most difficult models that are in our test set. So let's look at the performance improvements that we've gained moving from version 7.5, our most recent release, to version 8.0. So this chart gives a whole bunch of data that speaks to the performance improvements. I'm not going to go through every number in this chart, but let me give you a sense of how to read this chart. So along the rows, what we have is different types of problems, and in the case of linear programming problems, different algorithms that can be used to solve those problems. So for linear programming, we can solve those methods using the concurrent solver, the primal simplex solver, the dual simplex solver, or the barrier solver. And in each case, those algorithms have undergone some changes, and there are some performance improvements moving from version 7.5 to 8.0. And then we also have MIP models, mixed integer linear programming problems. We have MIQP models, mixed integer quadratic programming models, and MIQCP models, mixed integer quadratically constrained programming problems. And what we've done is we've taken our benchmark set and we've divided into two subclasses. So on the left, you see results for the models that take at least 1 second to solve for either version 7.5 or version 8.0. And on the right, we have results for models that take at least 100 seconds to solve using either 7.5 or 8.0. So the columns on the left, the 1 second columns, these are meant to capture the broad set of models in the test set. So we removed models that take fewer than 1 second just because those are probably trivial models, probably not so important how performance has changed on those. And then on the right, models that take more than 100 seconds. So this is meant to capture the harder models in the sets. So let's look at a specific row in this table. Let's consider, for example, the dual simplex algorithm for solving linear programming problems. So if you look at the results for models that take more than 1 second to solve, what you see is that the first number in that row says that there were 466 models in the test set where either 7.5 or 8.0 took more than 1 second to solve that problem using the dual simplex algorithm. Among those models, version 8.0 was faster on 110, and version 8.0 was slower on 61. And your reaction to this may be, well, how is it possible that the new version is slower on some models? This is just the nature of math programming. So no matter what change you make, some models are going to get faster and some are going to get slower. So if you insist that every change has to improve performance on every model, we wouldn't be able to make a single change to the product. So some models got faster, some models got slower, and on average, the dual simplex solver in version 8.0 is 12% faster, 1.12x faster than the dual simplex solver in version 7.5. So similarly, if you look at the models that take more than 100 seconds to solve, there are 171 models where dual simplex took more than 100 seconds using either version 7.5 or 8.0. 8.0 won for 77 of those, 8.0 lost for 31 of those, and the mean performance improvement is 31%. So I'm going to draw your attention to another row in the table. So the mixed integer programming, the MIP row, there were 2,263 models where either 7.5 or 8.0 took more than a second. And on average, version 8.0 is 16% faster than version 7.5. And for models that took more than 100 seconds, version 8.0 is 26% faster than version 7.5. So why are these two rows in the table highlighted? Well, so the main reason is that these are the two most important algorithms in our product. So mixed integer programming, this is the most important just because it's the most widely used. So I'd say 80 to 90% of what customers do with our product is solve mixed integer programming problems. And with this release, the ability to solve mixed integer programming problems has improved significantly. So 16% improvement for the broader set and 26% improvement for the harder models in the set. The second row that's highlighted is the dual simplex algorithm. So it's an important algorithm for solving linear programming problems, and linear programming is still quite an important problem to solve. And another reason it's important is it's actually the primary building block for mixed integer programming. And so part of the improvement in mixed integer programming comes from the improvement in the dual simplex solver. So we were able to obtain a 12% improvement in dual simplex performance across the broader set and a 31% improvement across the models that take more than 100 seconds. And one thing I want to point out is that dual simplex is an algorithm that's been around for a long time, neighborhood of 50 years. And it's extremely difficult to get higher performance from this algorithm. So we're quite happy with these improvements in the dual simplex solver. A few more numbers in this table I wanted to draw your attention to. There are a few numbers that are grayed out. So these are measured numbers. These are the best numbers we have. However, we just don't think that the number of models in this set is large enough to really capture the broader performance change. So we've included the numbers in the table, but we just encourage you not to take them too seriously just because the size of the problem set, it just isn't that big. So now I'm going to look at the performance improvements from the last major release of Gurobi to the current release, version 7.0 to version 8.0. This, of course, includes the improvements from 7.0 to 7.5 and from 7.5 to 8.0. And as you can see, going from one major release to the next, there are pretty major improvements across the full range of algorithms and problem types. So, for example, dual simplex on the models that take more than 100 seconds, an 82% average improvement in performance. And for mixed integer programming on models that take more than 100 seconds, more than a factor 2 performance improvement. And so we're talking some quite major performance improvements. So to set these performance results in more of a historical context, this slide looks at historical improvements in performance for mixed integer programming problems that take more than 100 seconds to solve. And it looks at the improvement from version 1.0 to 2.0 of Gurobi, 2.0 to 3.0, etc. So as you can see, version 1.0 to 2.0, roughly a 2.2x performance improvement. For version 6.0 to 7.0, almost a 2.5x, and for 7.0 to 8.0, roughly a 2.1x performance improvement. So we're averaging nearly a factor 2 performance improvement with each major release of Gurobi. And so the cumulative improvement is captured in the red line. So what we do there is essentially we multiply the performance improvements for each release together to get a sense of how our latest release would compare to release 1.0. And if you do this, what you find is that over the 8 years between our current release, 8.0, and version 1.0, the cumulative improvement is right around a factor of 91. So, and a factor 91 really is transformative. It really makes it possible to solve models now that you couldn't even dream of solving just 8 years ago. So to summarize, our 8.0 release includes significant performance improvements, significant new features, and ultimately we hope it has something for everyone.